Dear students, now we will discuss about the phasor relationship for circuit elements. You can see here there are three elements are used here in AC circuit analysis: resistor, inductor, and capacitor. And most probably the use of these three things, because inductor and capacitor are the frequency selective components, and so that has been used in the AC circuit analysis. As you can see in the register, in AC circuit the frequency domain and the time domain, they are remain same. So the voltage and current are in same phase, so in same direction. That has been written here, it has been drawn here in phasor diagram, and it is the phasor relationship, phasor form of voltage V is equal to RI and phi, and there is a phi that is in phase, so that is in same direction. It has been written in same, it has been drawn in same direction. If it is an inductor, so it is governed by this equation, L di by dt. As we know, the voltage across the inductor is equal to the inductance into di by dt, the change of currents. And for that we know Fourier transformation, we can get the frequency domain. V will be vector V, and ddt will be j omega, and L is as we know that L is constant, so j omega Li. I is also a vector in Fourier transform. After that we can see here the phasor diagram of inductor, that I lags V. That means voltage is leading and current is lagging, and both are in 90 degree in each phase. In an inductor, voltage and current will be 90 degree out of phase, but you have to know that voltage is leading and current will be lagging, so current is drawn in the below of the voltage. And there is another thing, for the capacitor, assume the voltage across the it is V is equal to Vm cos omega t, and in capacitor we know that the change of voltages in time, which means differentiation of voltages and capacitance, get through to this I. We can just reverse direction, we can just reverse it and make it like that, or make a Fourier analysis. We can get I vector is equal to j omega, ddt means j omega, d by dt, cv. This v will be vectorical, and then we can get v is equal to I by j omega c, this equation. This is the voltage current relationship of capacitor. And now we can see the capacitor here, same here. Current, the phasor diagram for the capacitor, I leads V, that means capacitor, C for capacitor, C for current. So you have to keep on your mind that current will be leading than voltage in capacitor. And there is another relationship you can see here. For this you can make a screenshot of it, the RLC, the relationship of their time domain and frequency domain. That's the voltage current relationship. There is some maths, but that's not so much important, but you have to keep on your mind the math of the impedance and admittance. What is impedance? Impedance means the Z of a circuit is the ratio of the phasor voltage V to the phasor current I, measured in ohms. That is measured in ohms. That is known as impedance. If a resistance and the reactance both consists the impedance, you can see here a lot of impedance and admittances. And admittance, as you know, that is the inverse of resistance. If it's R, admittance will be 1 by R, and vice versa. You can get all of the things. I have given you a question about that relationship of the equivalent circuits at DC at high frequencies, inductor, capacitor. How does it really behaves at DC, short circuit at DC? As we know, frequency will be 0, so that will be a short circuit. And in high frequencies, the inductor will be open circuit. Capacitor is the vice versa of it, opposite of it. The capacitor open circuit in DC is open circuit at DC, and high frequencies it will be a short circuit. And admittance, so is the reciprocal of impedance measured in Siemens, as we know. And Z can be found out by these equations. We can find out the theta and the Z by this equation, that is preliminarily known as the vectorical equation, R square, resistance square, plus the reactance square. And the angle will be the x divided by R, reactance divided resistance. There are the other things, the conductance and other reciprocal relationship of it. That's an important math that you have to keep, that you have to do in your home. Find VT and IT in this circuit shown in this. That's a series circuit, and we can find out this the 0.1 farad, 5 ohms, and first of all, that is the VS. This source voltage will be 10 cos 4t. 4 means that is omega t. We can get the omega from it, so the 4 are here. So the impedance we can calculate by this. That's a series circuit, so 5 plus, that is capacitor, that is the j omega, that is R minus jc, and from jc we can get 1 by j omega c, and by this we can calculate the current. And also there is an important part of current I will Vs divided by Z, and just calculating these things. First of all, make it to the complex number, then you can also calculate it through to from R to Z from polar transformation. That's means Z to R and theta, and voltage across the capacitor is IHC, same. Current will be same here, current will be same here, it will be same here. This series circuit, so we can get this, and also we can find out the equivalent converting I and V in equations 9.9.1 and 9.2. That means these two equations from I and V, we can easily get these equations. How can we get? Previously I have shown you one thing, that these equation, that is V, and these equation I, these two equations can be converted as omega is 4, so cos 4t plus 5 means this is 26.57, and another VT will get minus 63.43 degree, and the previous conversion we get this. There's another math you have to do here. I have to erase it, just to erase these things. Okay, just you have to do this practice problem in your home. That is an assignment 9.9, and that is an assignment, and after that you have to do some other maths too, Kirchhoff's law in the frequency domain of time domain. So thank you very much for being with me, and next time we will know the basic parameters and other applications in AC circuit analysis. Thank you very much.